even the first petaflop system in China. So all of those are very important milestones in Chinese HPC history. The main research areas in NUTT can be divided in the following three parts. First is parallel architecture of HPC. We have developed various architectures of HPC, set vector, SMP, MPP, and cluster or hybrid system. And also the stream processors and also domestic CPU. And we have done a lot of research work and implementation work for the high-speed interconnection network. Yeah. And the third part is for the system software, meaning for the new concept of OS for the general purpose users, and also for the HPC custom and runtime system. And HPC language and programming models. The third part is focused on the computer applications. We focus on the HPC applications and parallel algorithms, as well as the cloud and the grid computing. So it's an overview of the HPC research in NUTT. So I think we can find many points to the further collaborations. Now the retrospect of the Tianjin. As Professor Chen mentioned this morning, the Tianjin has a hybrid architecture, CPU plus GPU. And the peak performance is 4.7 petaflops, and the link pack performance is 2.57 petaflops, with the power consumption around 4 megawatts. And it was the top one in November 2010. It's from chips to the entire system. In fact, we use Zen CPU with 6 cores, and also the NVIDIA GPU M2050. And partly we use our domestic CPU FT1000. And the CPU and GPU integrated to combine as computer nodes. The whole system connected with proprietary interconnection network. And also, we use a custom global file storage system. The whole system totally have more than 180 cores, CPU and GPU cores. So for the hybrid architecture supporting, besides the hardware design, the mainboard design, the rack design, we also focus on the system software to exploit the hardware system performance and scalability. We developed the resource management with the accurate scheduling. It could allow the top load and allow the task distributed in the CPU or GPU. And we also use the hybrid programming model. In Tianhe 1A system, we use MPI plus OpenP plus CUDA and do many compiler optimization. Such as adaptive partition and soft flow pipeline and ability scheduling and sentinel state transport and computing, and also select some optimization in the communication network. All of those aim to balance the workload between the CPU and GPU, and also overlap the computing and data transfer between the host and the GPU device network. And also to optimize the load balancing and also the scheduling between the three migration and also some optimization for the communication network. So with this efforts, we have improved the efficiency of the whole system. For a single node CPU with GPU, we could get more than 50% efficiency. For the whole system, the impact ratio is around 50%. As we all know, the interconnection network is a key issue for large-scale supercomputing system. In NUDT, we have developed more than 4 generations of our proprietary interconnection network. In Tianjin, we use our proprietary interconnection we named Tianjin. This is a metric of the Tianjin. We use hierarchy factory structures, the 2-level hierarchy factory. And we also developed the 2 kinds of the chip size for the interconnection network. One is for the network interface, NIC, which supports RDMA as well as MP communication. And with the hoster interface, we use 16 lines PCI Express 2. Yeah. And another chip site is a high-redax router. We call it NRC. In NRC, we implement many communication protocols in Part1 level. And also the credit-based floor control and the warm floor switch, and also the source routing. And the whole throughput of the single NRC is reached to 2.56 terabit per second. To the performance, the Tianjin node-to-node bandwidth is 80 gigabit per second, and the latency is 22 nanoseconds. For the whole system level, the aggregate bandwidth is 1,146.88 terabit per second, and the bisection bandwidth is 307 terabit per second. We also implement our own interconnection switch, also the switch board and backbone board. Based on the Tianjin, we also developed our communication system. We call it Galaxy Express communication library system, which provided to our upper system software and also for the application level, the high bandwidth, low latency, and the scalable communication network. We also provide the packet and the RDMA mechanisms to support for the high-speed communication. And we use the distant factor Q trigger by the control packet. And we also support for the tolerance. About the API, we support the user level API. It's support for the MPI library or something else. And for the kernel level API, we support for the TCP/IP protocols. And we also support the GPU Direct to improve the whole system performance. And based on Galaxy communication system, we developed the MPI Galaxy. Yeah, this MPI could exploit the multiple channels approaches over the Tianjin net. So we could choose one of the channel, and we also could separate the channels when we meet different requirements of the application models. We also enhance MPI-IO from ADL level. So the MPI Galaxy, the bandwidth, it's 6.3 gigabytes per second. It's more than twice as MPI based on IB. Yeah. About the system software stake, the Tianjin includes the OS, the kernel, and also the communication system, security SLA, support the resource management, and also the file parent file system, and the compiler system, and programming environment, and visualization system. We look like this soft roll stick is just a traditional soft roll stick like other supercomputers have. What's the point? I like to say, for the software stick, we focus on optimization and the customization oriented our supercomputer architectures and to fit our users' requirements. Besides the hybrid programming model and the communication library I mentioned before, there are some other tips. We also developed a high-performance virtual zone we call HPVZ in our OS and the self-management system. It could provide the security of user state and also could provide flexible running environment for different users. Maybe this function can get some benefit when they use as the cloud computing for some tasks. Another resources management system, in fact, we use the custom Slurm by the LLM. We also implement a scalability enhancement of the large-scale job startup in our core systems, more than 7 sign nodes and more than 180 sign ports. And also the power well resource allocation. Yeah. About the global file system, we custom the master. Yeah. We focus about the global file systems. We focus on the capability and the performance and also the reliability. For the performance, the core global file system bandwidth, the collective bandwidth, is more than 100 gigabytes per second. For improve the performance, we do some special protocols. We custom the file system protocols over the Tianjin. Yeah, it's more high bandwidth and low latency. And we also do some complication release for the currency accessing and fine-grained distributed file load mechanism. And we also do some optimization for the file cache policies. All those could extremely improve the performance of the and the scalability of the global file system. And also for the reliability enhancement, we do some fault tolerance of network protocols. So we exploit the Tianjin, the support of the fault tolerant routing and some protocols to support the file system protocols more enhancement. And the date, we have designed some new date object placement aim for the fault tolerance and aim for the reliability of the file system. We also implement the soft rate in the last year. So you can see I gave a brief retrospect of the Tianjin system. Now, nowadays, the supercomputer in NUDT, or even in China, our principles is practicality and the usability. So we also we use some mutual technologies to issue the core system correctness and the functionality. And at the same time, we focus on the optimization technicals and to improve the core system performance, scalability, and reliability. So there are very interesting debates focused on the demand-driven with the supply-driven. In the HPC field, that means whether it's a requirement of application leading the HPC system development or the HPC system development lead the application development. We especially in China, some people criticize that why we need the petaflop system or even to exascale system. For example, in China today, the application is far behind the HPC system development. So in our view, we are we are focused on the positive reaction of the application from various science and technologies leading by the HPC system. We have some interesting discovery based on the past 18 months from the NSCC Tianjin and also from the NSCC Changsha else in China. We found a very interesting changes of the parallel application scales. We can see that. Now, for the CPU only, the application parallel scale, there are more than 47% applications could scale more than 1,000, and that figure will be 12% at 2009. And also, there are more than 22% applications could scale more than 4,000, and also it's this figure is 5% at 2009. Now we have 25 applications could scale more than 10,000 cores, and has 6 applications could use the 4 systems with more than 80,000 cores. That couldn't be made before. And for the CPU plus GPU application, you can see there are more than 30 applications could use CPU and GPU hybrid in different scale. The maximum scale, it could use to 4 systems. There are totally 180,000 cores, CPU cores and GPU cores. And we also have 10 applications on the way. We are holding optimization the applications to the 10 level. So by the CPU and the GPU application development, I would like to say now most of people do the optimization work for the original algorithms or do some coding work. In our view and in our experience, maybe we need some new and creative design method for the CPU and GPU algorithm. We should rethink and redesign the 4 algorithms to exploit the large data parallel paradigms for the GPU system. So it will need maybe a long way to go with the collaboration of the science and the system software development scholars to put a joint effort to use the CPU and GPU hybrid system better. Now, in Tianjin, we have more than 300 groups of users come from universities and academic institutes, and also the industry enterprises and the business. So we have confidence in why we have still pursue the higher performance supercomputer in the next years. So it's a Tianke roadmap in the next 5 to 10 years. After the Tianke made this, we will be developed about 10 petaflop system around 2014. It may be a demonstrate system for the key technologies and used as an application platform for next generation system. Because the Chinese government the most launched a new HPC project during the 25-year project. It's aimed to, at the end of 2015, we will deploy a 100 petaflop system. In general, we prospective, we will have access scale system around 2020. Now, NUDT have deployed 2 supercomputer centers. One for the SCC Tianjin here. It's around November 2011. Another supercomputer center is here in Changsha. It has been on service since July next year. This system is a peak performance of this supercomputer center. The Tianjin system is 1.6 petaflop system. And the next one may be around here. It's for the next generation Tianjin. So we will have the north, middle, and south for the supercomputer center. So the prospect of next generation of Tianjin system, we will face many challenges in the architecture, in the scalability, and the performance, and also the programming. We will focus on the heterogeneous parallel architecture and the interconnection network and hierarchical storage system and the autonomic fault tolerance management and domain-specific programming frameworks and adaptive parallel computing. We will still focus on develop the high interconnection network. The goal is to support more than 100 SOM nodes and use a high-redux parser market multiple dimensions. And also the bandwidth will be improved a lot, and we also do some enhancement on the collective communication. And also we have developed and do much research work in the new enabling technologies, for example, the optical connections. Now we have developed the optical interface between processors, and another optical switches between CPUs is under research. In fact, we still need to do some evaluation of the feasibility of the optical connections used in the large-scale systems, and also the cost efficiency may be considered. So now we just can see that the optical connections may be alternative choice for next generation of Tianjin system. So I will be quick. And this is a large-scale hybrid tile system to scalability achieve the goal with 1 terabyte per second real bandwidth, and also focus on the usability and the flexibility. And for the increments of the reliable issues for the large-scale system, we will develop a resilience computing framework. The aim to collaboration with the whole system software stake to support various parallel application models. And to deal with the complexity of the tablet system, large system programming issue, we will develop the parallel programming framework. It could bridge the application developers and the hardware developers. So for user, it could hide the complexity of the programming. For the developers, it have an optimization interface. So they can, through this framework, the application developers and the system software developers could focus on different aspects and put a joint effort to make the application scale more large and to accelerate the application development. They'll also have some debates on the special purpose or the general purpose for the next generation extra large scale system. In our opinion, or in our project, the next generation tanker system is the general purpose. Although we still choose 5 priority fields of application. There are climate and learning, biomedicine, new energy, equipment management, and animation. We want to get some useful information, useful experience of this priority fields application development to give the other applications some hints. So I would like to give the summary. So for the next generation of tanker systems, we will need some creative HPC technologies in architectures and the hardware and software. And we also will need the hardware and the software and application core design. And we will strengthen the international and international collaboration. That's why I think that's why we are sitting here together to exchange and share our ideas. Thank you.
Thank you very much. Thank you very much, Professor Lu, for this really interesting talk. Are there questions? I have actually one. The next generation file system, do you still use Lustre as a core, or will it be a total new Chinese development?
No, we will have a totally new development, but we could use Lustre as one level, as a shell file system.
Thank you. More questions? Okay, thank you very much again. So now we continue in the programming area, and we have our talk from France. The replacement, Mr. Rosler. Sorry, I forgot it. Okay, Mr. Folio from the company CUPS is giving us an introduction into programming multi and many cores using directives.
Hello everybody, so I replace François Renaud. Already I apologize, he couldn't be here today, so I replace him. I will be based in Shanghai actually from this month, so I just arrived in China, and we will set up a small team about R&D and as well for customers in China. So it will be interesting to participate here. So I will talk about what we are doing. So mainly programming heterogeneous mini-core architectures and mainly using directive-based approach. Just a few words about CAPS company. So we have a 10 years of expertise in compilers technology. So CAPS is a spin-off of 2 research teams in France. And we were working before on CPU optimizations. Today what we are doing is we are working on GPU like CUDA-like architectures, and we are planning to go furthermore into mini-core architectures. And what we want to do is to find some solution in order to program this kind of architectures. We are based, so it's mainly based in Rennes in France, and we have an office now in Shanghai, as I said before, and we have some just a sales office in the United States.
Thank you.
This is just some partners that we work with. So we work with a large number of partners, some universities, and as well as some customers from different industries that are interested mainly in HPC fields nowadays. We are participating as well to European R&D projects because there is not so much software solutions in order to program heterogeneous architectures nowadays, and we feel it's really important to participate in this kind of project. So this is just a list about what we are doing in Europe. Things like teraflops, which is exploiting data flow parallelism, so it's a completely different way to think about how to program parallel architectures. We work as well with H4H project, which is helping, mostly for us, is developing and helping specific domains people in order to program parallel architectures. So we try to give them the expertise that we've got to do such things, and as well to get their feedbacks in order to improve tools to this kind of architecture. Alphonse maybe already speak a bit about it. So, and also Tune, I will present you later on what we think will be good for exascale architectures. And we believe in auto-tuning, so there is a project, European project, that is doing that. Mainly, the main aspect is you have an application, you put some directives, and then it will find an optimized way to go to one specific architecture. As well as Pro Asian PT, which is much more for the runtime support of such architectures in one way. And we just begin as well to do some R&D with for the China side. So we just began a MOU with Tianjin, and where we did it began just beginning of April. So we did one training for directive set based, and we got to continue this way. And the second thing is we opened what we call HMPP Competence Center, so which is involved to help people to go to heterogeneous architectures in collaboration with Shanghai University. Okay, so now let's talk a bit more about technical things about programming heterogeneous main code within Tianjin. So we have a big problem, let's say, with this kind of architecture. We want to get some portable performances. You want to write your code, and then for the next architecture, you will get at least the same performances, and you hope better performances. But you want as well to just write your codes just one time, if possible, and just in one language. Because if you have to learn one new language every time you change architecture, it will cost a lot of money, it will cost a lot of time as well. And as we've seen this few last year, we are accelerating of changing model. So every time you have to change a machine. If you have to reprogram, it will be really a big issue. So this is based on this aspect. We try to find some solutions in order to answer that. What we have seen for what we have done until now for legacy applications, they are mainly written in C, C++, and Python. They are using some custom code, and with combination with some library codes. There is like FFT, everybody do some FFT, so it's not useful to write sometimes your own FFT, except if you want to go to one specific architecture, things like that. This kind of application long for many years, for at least 10 years, let's say. So that one machine don't don't last 10 years. So how can you keep your code and to just run for a new machine? That's the purpose. So I will just review a bit about many core architectures. Why when I speak about many core architecture here, I focus on one node. Well, I don't really focus about MPI or several nodes matching. We just focus on optimization about one node. But there is many threads now in one node, so it's something interesting for a lot of aspects. I will speak about the directive-based approach. So we have nowadays several languages that permit you to access a GPU like OpenMP, basically. We have OpenSCC, so you put, like OpenMP, you put parallel directive and you can go to GPU, almost. We have HMPP as well, that do the same. I will talk a bit about how to integrate libraries. There is several libraries, like once again for F50 you have several implementations, and maybe the API is not exactly the same. So how we can combine directive sets in order to integrate libraries. And then I will speak more about what we plan for future or roadmap and why we believe in auto-tuning. So many core architectures nowadays looks like a bit this chain. So we have basically one GPU with a lot of threads combined with a multi-core CPU. And the links are really important and different. You have typically a GPU is really far from CPU, and you have to deal with that. You don't have the same memories. It's something that you have to deal with that before you didn't care so much. So, as well, this heterogeneous model is not fixed and is changing. We don't know, basically we don't know next matching what it will be based on. It will be maybe NVIDIA ATI GPU or just x86 multi-cores. We have as well some models like Intel Mike, which integrate a lot of x86 cores in one hardware. Based on that, what we want to do is to get some portable performances without betting which will be the next system. So, for the moment, what we've got is we've got several languages that try to target some specific model, some specific parallelism, that it's hierarchy. There is big hierarchy, so all of them cannot access to every target. What we try to do is to get a generic language that permits you to access this kind of target, all this kind of target. And that's why, as well, we believe in auto-tuning. If you add some nodes in your system, or if you change parallelism model, parallelism architecture, then you will have certainly to rewrite, to retune your program in order to get some performance. The more you optimize your code, the less it will be portable for another architecture. We can think as well about cloud computing. If you go to cloud computing, maybe you don't know which kind of architecture we get at the end. So auto-tuning will be something important in order to address a target which is not fixed. So how we do nowadays? So directive-based approach, it's a supplement to an existing serial language, which means that you don't have to rewrite or to learn another language. It's just some directives that you put, and you keep the serial semantic. So it's something as well important if you want to debug. If you want to debug on a parallel application, there is a lot of tools, but it's not as simple as debugging serial code. So to keep the serial semantic can be really important asset for the code. There is many variants that exist for this directive-based approach nowadays. There is HMPP, so that's what's CAP's product. PGI accelerator directive set, which is an equivalent of HMPP by PGI company. Open SCC, which is standardization effort in order to produce a directive set to GPU architecture. It's a consortium between NVIDIA, ATI, CAPS, PGI. There is no ATI, sorry, there is a CRE. And we produce as well there is OpenMP accelerators extension that exists for that, and OpenHMPP as well. We'll put it here, which is another effort to make some standardization. The purpose of that is just to get something that lasts for many architectures. About OpenACC, so you just use some few directives in order to get to the GPU and to manage data transfers. How you move your data between your CPU cores and your GPU cores. So the main idea is you construct some parallel and kernel regions, parallel loops, to design your parallel hierarchy inside your serial application in order to go. We can see it's a subset of HMPP. I will show you why later. It's very good to get that as a standard. So the main approach for that is you got a mirror. You got a mirror. It means that you got your memory inside your CPU, and you design a pointer in your GPU, which will be a mirror of your CPU. So it's in order to ease transfer. This is something that will be important in order to go to future architecture, because data transfer nowadays it's something really difficult to optimize, and it can take a lot of time to go to GPU just because of that. So it's an important point. And basically after that it's work, let's say it's work exactly like CUDA. The model behind that would be like CUDA. So you have GOM, which is a group, and workers, which are threads. You can go to vectors if your hardware supports. So the main idea is really to support many, the whole hierarchy of parallelism, except for just one node. So we will say that. And so we did an experiment in order to figure out if we can use OpenACC in an effective way. We did it with Jiaotong University in Shanghai. We get, for instance, for this application, which is DNA sequence computation, we get 13, a speed up of 30. So in really few weeks. So it's really efficient actually. So HMPP is what we do nowadays, and based on this technology, we improve in order to go to future architecture. Basically, this is the same model of programming. You just put some directives in your serial code, and then you can go to GPU. You have a source-to-source engine, and we rely on the constructor in order to get a real compiler to get optimized start, optimized time. We provide more things that will be important. So multiple device management, which is improved way in order to get multiple GPU. Multiple GPU on one node how you allocate resources, what can you do with it, how you move data, things like that. Library integrations as well. If we think about new applications, library integration could be really important. If you want to combine several models, if you want to simulate very transversal simulation, you will certainly need a lot of library integrations. And there's still a lot of work to do on that. We provide as well, which is compilers, techniques, loop transformations, directives that could be very useful if you think about auto-tuning. So, yeah, library interoperability, so I already speak about that. So let's speak more about how to go to auto-tuning. What we need is to create an optimization space to explore, which means that there's still a user behind machine that say, okay, I know my application, and this is the iteration space that I want to explore. And then you will have a runtime that just finds the best way to go to one architecture based on transformations, compilers transformation. That's the main idea of what we are doing now. So just basically. So we have what we need is this directives and this transformation code, and we strongly need as well some feedbacks from the runtime and from applications. So performance tools in order to know which resources are used, which is the performances, and things like that. And we want to combine a system that do this loop, that code generation, and then we get back some feedbacks in order to improve. It must be set as well as an exploration tree or things like that. There is many questions still remaining in order to go to this, to finish this auto-tune. This is what we see for the moment as the global auto-tuning infrastructure. So we have the application code. We have what we call a codec finder, which is a tool that permits you to find the parts that you strongly have to go to GPU or to another accelerator. So it finds characteristics of your hotspots in order to know if they can fit GPU and how to put them on GPUs. You go through this path, and so the compiler is a proprietary compiler, so basically CUDA compiler mixed with x86 compilers, for instance. And you get an executable program combined with auto-tuning, and then based on this object, you can put on in ordering every architecture, and you will find the optimized way to go. So we already get some results concerning this architecture to go to auto-tuning. But it's still in work, and we still have to work on that. So, yeah. So what we plan is to go to a standard auto-tuning interface. So we try to find a way to have a complete tool sets that permit you to last for many years for your architecture and to ease programming of this kind of heterogeneous architecture. That's it. Have you got any questions? Thank you.
Thank you very much. Questions?
So you haven't mentioned your initiative open HMPP in your talk. So
Sure.
can you comment on how serious you are with that proposal?
Yeah, sure. Okay. So yes, I have just few things about
Oh, sorry.
about OpenHMPP. I just went very fast on it because what we want to do with OpenHMPP, so it's a consortium, and we completely open the directive set, so everybody can implement a free tool using what we have done as directive sets. Let's say it's a concurrent of OpenACC. You have two different ways to program, some subtleties ways. And yes, we believe really that OpenHMPP can be something good if there is enough support after because we can include in it some more research things, more smart ways to program. Yeah. So for the moment, OpenHMPP, so we developed HMPP with CAPS, and there is one more company that is doing directive sets based on OpenHMPP. The company name is Pascal. I don't know if you heard about it. So if you want to join OpenHMPP, please contact us. If you have any ideas to improve, it would be very easy.
So HMPP is not that, but I guess OpenACC has higher priorities, or?
So OpenACC is a really good standard. So we put efforts really in order to get some standards, because what we want is something that lasts. What we provide in HMPP is basically OpenACC plus some other tools around. So OpenACC will be, let's say, like it will be just a directive set. And what we really focus on in those days is, for instance, tools like auto-tuning and just to get a whole set of tools that permit you to program, not just the directive set.
More questions? Okay, thank you very much again. So our next speaker is from Yan Wai-Chu. He will give it out, biological medicine.
Ladies and gentlemen, from Shanghai Institute of Chinese Academy of Sciences. Today I'm going to talk about using Tianjin to carry out molecular dynamic simulation, MD simulation. The topic is structure-function relationship of drug targets, microsecond molecular dynamic simulation. Proteins are the chief actors within cells. They carry out the duties specified by the information encoded in genes. Flexibility or the dynamics is a key determinant for the proteins, for the biological function of proteins. There are various conformation changes within cells. The time scale may be varied from picosecond to nanosecond to microsecond and even seconds. The rotation of a side chain of a residue typically is about picoseconds. The other motions, such as the rotation of a helix or the flexibility of a loop, is a time scale of nanoseconds. Larger motions, such as the relative motions between domains and the protein processes, needs microsecond and even longer time. MD simulation is a technology to study the protein dynamics at atomic level. Theoretically, MD simulation could be used to study all these motions with different time scales. It depends on the computational resources. Among the proteins, hundreds of them are drug targets. Typically, a drug target is a molecule that involved in a particular metabolic or signaling pathways that is specific to specific disease or pathology. The MD simulation is critical for the mechanical study of drug targets and the rational drug design. Usually, the MD simulation systems on drug targets contain about 100,000 to 500,000 atoms. Previously, our MD simulation on drug targets is usually about nanoseconds. Based on Tianjin, microseconds MD simulation on drug targets now could get carried out to study the structural function relationship of drug targets. The microsecond time scale extremely broadens the application of MD simulation, of the application of MD simulation on the study of drug targets. Here, I give two typical applications of using MD simulation to study the function structural relationship of drug targets. The first one is using MD simulation to provide more abundant confirmation samples on drug targets so as to study the mechanism. The second application is about using MD simulation to get more accurate structural model for the ligand binding. Is to replace the study of crystallography. These are the first applications. The topic is conformational transition and the energy landscape of ARBB4 activated by neural one beta. ARBB family receptor tyrosine kinases play fundamental roles in controlling cell proliferation or differentiation. This family consists of 4 members. These members share similar structural arrangements and similar activation mechanism. Each member consists of an extracellular region and a transmembrane domain. It has single transmembrane spreading domain, cytoplasmic tyrosine kinase domain, and a circumference domain. The receptor is activated by the ligand binding. The ligand binding inactivates the receptor, then the activation of the receptor thereby triggering the downstream pathways such as those based on MAPK or PI3K. Crystal structures for the extracellular region of the ERBB proteins have been obtained. The extracellular region contains 4 domains. Domains 1 to 4 are colored in blue, green, yellow, red respectively. This 2 one, the first 2 is about the inactive state. It's the unlikely inactive, which is likely inactive. These 2, the last 1 is unlikely active and likely active. You could see that the arrangements of the 4 domains are very different between the inactive and the active states. In these inactive states, domains 2 and 4 form a tether between them. The opening of this tether is a key structure parameter for the opening of the extracellular region. Although these crystals cast inside for the confirmation of different states, but we have never observed the exact activation mechanism of this region. As a result, the detailed mechanism about the activation mechanism is still unclear. For example, about the detailed roles of the ligand binding is not clear. In fact, there are 2 different mechanisms about the role of the ligand are presumed. The first one is that the first mechanism suggests that the ligand shifts the spontaneous conformational transition equilibrium of ERBB4 by trapping the receptor molecule in inactive state ready for dimerization. In this mechanism, the ligand is not the driving force for the conformational transition of the extracellular region, while the second mechanism suggests that the ligand binds to and promotes a dramatic conformational change of the receptor. We do not know which one is right. To answer these questions and to obtain more detailed information about the activation mechanism, we carried out microsecond MD simulation on ERBB4, a member of the ERBB protein family. We carried out 2 systems. The first one is about the unlikely inactive. It only contains the apo ECR region of the ERBB protein. The second one is likely inactive states. And the general ligand neural beta was put into this system. During the simulation of the ligand system, the conformation change from inactive from inactive to an active-like state was observed. Whereas this kind of large-scale motions have not been seen in the unlikened system. Therefore, it could be concluded that the likened binding indeed is a driving force for the conformational transition of the ECR region. Therefore, the second mechanism is right. This movie is about the dynamic processes obtained in the simulation of the likened system. In the beginning, domain 2 and domain 4 form a tether, and then the tether is opened. Our simulation suggests that the distance between domain 1 and 3 is become closer. It's because two kinds of motions. The first one is about the rolling of domain 1 over domain 2. The second is the bending motion of domain 2. Particularly, the bending of domain 2 is very important for the disruptor of the tether. MD simulation also suggests the driving force for the conformational transitions induced by the likened binding. Electrostatic analysis suggests that in the Apple ECR structures, the gap is about 60 angstroms. After the likened binding, the gap decreases to about 30 angstroms, but still not allowing the direct interaction between the likened and the domain 3. Electrostatic surface suggests that there are negative charge residues in domain 3, and the likened contains 3 positive charges. As a result, it is the electrostatic interactions is the driving force for the conformational transition. Based on the MD simulation trajectory, principal components was analyzed. The principal component analysis suggests that there are two major motions is formed between the domains. The first one is about the separation of domain 2 and domain 4. The second one is the opening rotation of the domain 1-2 pair and the domain 3-4 pair. Our simulations on the likened system suggest that has addressed the conformation transition from an inactive state to an active-like state. This MD trajectory contains a broad range of conformations that sample around configuration space, therefore providing enough conformation information for an energy landscape analysis. Based on the principal component analysis, showing the energy landscape analysis, we used the distance between domain 2 and 4 and the graph angle between domain 1-2 pair and the domain 3-4 pair as two reaction coordinates. The energy landscape consists of 2 deeper and a shallow one. It's very interesting that the starting structure is located half above the wall, broadening the first layer. Along this pathway, the complex moves down to the first energy layer. It is the first stage of the conformational transitions. Then, by climbing an energy barrier of about 2.7 kcal per mole, the complex reaches the second shallow layer. The energy barrier is consistent with the experimental experiments that showing that the tensor of ERBB1 contributes about 1 to 2 kcal per mole to stabilize the inactive states. The complex stay in the second layer shortly, and then is crossed over a low energy barrier to reach the last layer, so as to reach the active-like states. According to the MD simulation results, the dynamic processes of the ERBB4 activation now could be presumed. It could be found that the likened binding induced a conformational transition of the extracellular region of the receptor, so as to promote the activation and the dimerization of the of the receptor, leading to the activation of the intracellular paths, and thereby triggering the downward pathways. As a conclusion for this path, ligand binding is the active inducing force for the conformational transition and further dimerization of the receptor. Induced by the ligand binding, domain 1 of ERB4 get close to domain 3 through two motions. The agreement between the estimated energy barrier for the tether opening and the experiment implying that the reusability of the conformational transition pathway. The proposed atomic mechanism for the ligand-induced activation of ERB4 also provides clues for studying the activation mechanism of other ERB proteins and for designing new therapeutics for targeting these receptors. Usually, rational drug design on ERB proteins usually is targeted on the intracellular parts. Our study suggests that we also could design some chemicals to target the conformational transition pathway of the extracellular region. The second part is about using MD simulation to aid the rational drug design. We study about the topic is a structural model for SCC-KoM binding and the rational drug design of new activators. Ion channel is one of the ways for ions across membranes. Ion channels allow the ions flow down to the electrochemical gradient. Ion channels are prevalent in membranes that surround almost all biological cells. Ion channels play important roles in living organisms. In fact, human beings are run by electricity, and the ion channels are the core of the electrical system. Ion channels play pivotal roles in many physiological processes such as heartbeat, muscle contraction, hormone secretion, visual and olfaction, pain, and cognition, etc. There are many chemical and genetic disorders that could disrupt the normal functions of ion channels and have disastrous consequences on the organisms. Genetic disorders of ion channels are known as channelopathies, including muscle system-related disorders, neuronal disorders, kidney disorders, secretion disorders, urine disorders, and so on. So, as a result, ion channels are important drug targets. In fact, it's the third important drug targets, only after GBCR and kinase. There are abundant antagonists have been widely used for hypertension, arrhythmias, seizures, and neuropsychiatries. The lead targets include KCQ2 channel, NAV1.7, and the TRIP channel. Ion channels could be classified according to the gating mechanism. It should be ligand gated, it also could be mechanism sensitive, it also could be body gated channels. Ion channels could also be classified according to the ion selectivity. It could be cation ion channel, including sodium channels, calcium channels, potassium channels, etc. It also could be anion ion channel, such as chloride ion channel. Over 400 genes in human encode ion channels. Among them, at least 167 of them are encoded potassium channels. Potassium channels contain 4 kinds of structures. The first is, this one is 2 transmembrane segments with a core region. This one is 6 transmembrane segments with 1 core region. This one is 8 segments with 2 core region. The last one is 4 segments with 2 core regions. Voltage-gated potassium channels are the most abundant potassium channels and the important drug targets. They belong to these structures. They contain 6 segments with 1 core region. There are abundant KV channel inhibitors are available. This is a typical structures for the activator for the inhibitors. The mechanism and the target sites of inhibitors are clear. Usually they contain usually there are 3 typical targeting sites: the outer pore blocking region, and the inner pore blocking region, and this site. However, we have not get structure information, get the structure information of inhibitor and the cable channels. We only used homology model structures to get the structures and carried out rational track design to find inhibitors. Very different from inhibitors. The activators of KV channels is still lack. There are only few of them are available. Furthermore, in fact, the study of KV channel activators is a famous difficulty of pharmaceutical research. The binding site is not clear, and the structural model of ligand binding is not available, and there is no structure-based rational track design was carried out. KCNQ is the seventh member of voltage-gated potential channels. It contains 5 members. KCNQ channels play KCNQ channels mediate substructure code non-inactivating voltage-gated potential current, such play inhibitory role in controlling the neural excitability. KCNQ channels are the lead track targets of KV channels. ZDZ is a typical activator of KCNQ channels. It could be used as a chemical probe for the study of the activating binding site. In this study, by combining use MD simulation and the molecular modeling and the mutagenesis electrophysiological combination, we first validate binding site in the VSD region of KCNQ channel. In fact, this binding site is the first validated binding site of a KCNQ channel. And then we construct a detailed structural model using molecular dynamic simulation. And the structural model was put into rational track design. The rational track design results could in turn validate the accuracy of the binding site and the structural model. Finally, 21 compounds were selected and put into biological assay. 9 of them in cellular experiments have been valid to be KCNQ activators. We also put them into in vivo study without any chemical modifications. 2 of them show significant anticonvulsant activity in mouse-induced model. Now it's conclusions for this part. With the critical help from the MD simulation carried out on Tianjin 1A, we identified the first activator binding site of KV channel, and then we constructed a structural model of the ligand binding using MD simulation. In fact, this structural model could replace the utility of the structure from crystallography study. Finally, new activators was obtained through rational track design. This study, in fact, it maybe is the first example of using rational track design to find activators of KV channels. It's also the first example to find activators of ion channels. Now it's the acknowledgements. We thank Zhao Binggao and his students Li Ping in Shanghai Institute of Material. We also thank my 2 students Yun Du and Zhu Qizhen. They carried out the simulation. We also thank National Supercomputing Center in Tianjin for providing computational resources. These projects are supported by National Science Foundation of China and the State Peak Program of Basic Research of China. Thank you for your attention.
Okay, thank you for the talk. Questions? I have actually a few questions. Can you tell us a little bit about the programming behind your research? Is it a MPI program? Are you using the GPUs for these calculations?
Oh.
How many cores are you typically using for such a simulation?
In fact, we need more cores on CPUs, but as cost effective, is very important for our study. We only have 2,000 courses, so we divide them to different. In fact, more courses is very important for these studies, but the cost is very expensive. So in these studies, we try our best to decrease our simulation systems. In future studies, in fact, we need larger systems to get more accurate results. So I think 10,000 course is usually appropriate numbers for the study of the structure function relationship on drug targets.
And how long would one simulation run?
The first study is about the first study was 1 millisecond. We obtained 100 nanoseconds per day. So usually we have to run about 10 days.
Question? What do you consider in the effect of water in the water?
Yeah, all is with order at all atomic level. It's usually about 50,000, 500,000 atoms, including water molecules.
And the interaction potential was local or?
Excuse me?
And the interaction potential was electrostatic or local or? The atomistic interaction potential.
The partition?
No. The atomic force among the atoms were they local?
We divide the. You mean how to divide the systems?
Well, the equation.
You can talk about. Huh? Oh, you mean the force field?
Yes,
Yeah.
Oh, it depends on systems. We usually use the last system we use charm force fields. The force is based on Newton theory.
Okay. More questions? And thank you guys very much. So we have one more presentation before our coffee break. It's Wu Wai. He'll tell us a little bit about oil exploration.
Okay, good afternoon everyone. I'm from BGP, China National Petroleum Corporation, and I think it's my great honor to share my report with all of you. In the following time, I will give you a short report on the application of geoselecting RTM on TH1A large-scale parallel clusters. I will divide my report into two parts. Firstly, I will give you a brief introduction on seismic imaging, especially an advanced imaging method, reverse time migration. And here and after, I will use RTM short target. And in the second part, I will give you an introduction on the application of geoeast lightning RTM on TH1A. Now that's the first part. Oh, there's something wrong with some pictures, but it doesn't matter. For now, as we know, with the increasing demands for oil and gas resources, we are forced either to maximize the production of discovered reservoirs or to explore new ones in complex domains. So, the more and more accurate seismic imaging is needed. Seismic imaging is the ultimate stage to produce accurate images of the Earth's subsurface that are suitable for interpretations by geoscientists. And reverse time migration is an advanced image method among the other ones. In this slide is the key procedure of the method RTM we put forward. After prepared the input data, we usually use finite different methods to simulate the source and the receiver propagations. And here we can see the difference between the source and the receiver propagation. Now we can see this timeline. The source will field the propagation we marked from 0 to t, and the reverse will field propagation we marked from time t to 0. And that is why we call this method the reverse time migration. And after this two wheel field are calculated, the correlation operation between the two wheel field can be introduced to make the ultimate images. In this slide, we can vividly depict the source of the instance wheel field propagation procedure. And we can see from here, there is only one shot stimulate at the same time. And when this shot stimulates, the time marked as 0. And in this slide, you can see the receiver or the reflection will field the propagation. We can see from here, there are a team of receivers stimulated together. This two slice is only the 2D model. So if we expand this model to 3D, it will be a large amount of data. And during the propagation, we need to store the snapshots by the time step we preset. After this propagation procedure finished, we can make the correlation operation to get the image. This is the first, the one-shot images in the whole survey. And from this slide, we can see the more shots, the more details we will get. As the number of shots increasing, the subsurface structure becomes more and more clear. And when the number of shots come to 513, we can see that the structure of the subsurface may be interpretable or reasonable for the geoscientist to make some interpretation. And here, I think we may have a brief understanding on the seismic imaging. Now let's move to the next part, the application of geostellating RTM on TH1A system. First, I must introduce what is geostellating. Geostellating is an integrated imaging software developed by BGP to realize the reverse time crystal depth migration. And it has a lot of advantages, such as the friendly user interface, high efficiency RTM operation, autonomous job control, and it also can run on GPU-CPU architecture. Here is the user interface of geostellating system, and we can see here a lot of details of the job running. You can monitor the node running status, the CPU usage rate, and other informations. Based on the states above, we can see the key features of RTM. The short image can be calculated individually. And secondly, finite difference methods are introduced to calculate the wave field propagation. The third one is the snapshot to store wave field. This will lead to a large amount of data storage funding. And the last one is autonomous parallel mode, which means high efficiency, balanced natural load, flexible resource distribution. When we applied our GeoEast Lightning RTM system on TH1A, at the very beginning, we must face some challenges. The first one is the snapshot storage. As I mentioned before, there is a large amount of data to be stored. Ordinarily, we usually use local hard disks to store this large amount of data. But as we know, on TH1A system, there is no local hard disk. So we made some solutions. We use local memory to instead of the hard disk to store this large-scale data. And we choose adaptive node parallel mode. That means that we can use a number of nodes to operate with one shot together. The number of the nodes will depend on the project you are running. And the last solution method is the high efficiency comparison algorithm. This will lead to a smaller data storage money, as we know. And this is also the solution to the I/O problem. And the second challenge for the RTM running on TH1A is the I/O problem. As usually in our system, when we run RTM, there depends on the amount of data. We usually use maybe thousands of nodes to accessing some files simultaneously. And this will create great pressure on the nodes and the I/O transfer. So we develop a job delivery control mechanism. We will set some time delay to send to the send job. And we also develop some storage stripping system to limit some job to a certain strip of storage. And the last one is the job schedule system. As we know, TH1A has its own Tianhe job schedule system, and our software has our own. So we must make some mix with the two kind of job schedule system. And for now, we run the project in both Inferon and Lightning job schedule system. And in the future, I think we may develop some adaptive method to run the job only with Inferon. This is the list of the projects we have done on TH1A system. From November 2010, we have finished 3 large surveys on this system. And the latest one is 2,600 square kilometers. And the seismic data amount to 2.2 terabytes. There are about 220,000 shots, and we only use 2,000 nodes. Use 60 hours to accomplish the projects. This survey is the largest survey for running RTM for the time being. These 2 slides is the result we get acquired on TH1A system. And at the end of this report, there are 2 groups of comparisons between Kirchhoff and RTM image method. And I will say first, Kirchhoff is the much simpler imaging method, as the hardware and the parallel system developed, we can make the imaging much accurate. And that's all my part. Thank you for your attention.
Thank you very much for this very interesting talk. Questions?
I'm not so good at remembering numbers. So you say you use 7,000 nodes. So this is almost a full system, isn't it? Or is it is a full system?
This line,
Almost a full system.
Almost full system.
yeah.
Have you also used the GPUs for this program?
Not yet.
Not like
A little bit more.
the Fourier transform, that should be a good candidate for
GPU
running on the GPU.
也用了，
No.
没有。
So far, we haven't run any GPU version on T5 system, but we have a stable version of GPU software just released, and in the future, we will definitely run on GPU version on T1A.
Very interesting. Other questions? Okay, thank you very much, and you gave us some extra time for coffee. So we have a coffee break now, but I think because we are early, we actually can continue at 5. Sorry, 4. 4, yeah.
Okay.
Four.
Yeah, thanks for saying our host invited us all to have a picture taken at the reception hall. So let's all go there.
How long?